Hello, thanks for clicking and welcome back to another Anarculus production. Today we have reached the end of chapter 1 and we are going to talk about limits at infinity, the last type of limit that we have not discussed. Okay, we've discussed what happens with an algebraic limit if you get 0 over 0. We decided that was an indeterminate form. You needed to figure out WWA A1KD. What would an algebra 1 kid do? We also discussed what happens if you get a number over 0, right? That means you're going to get some kind of infinite limit, or the limit perhaps won't exist. Today we are going to talk about what happens if you're going to calculate the limit as x goes to positive or negative infinity. All right, so the first thing we can do is we actually defined earlier about a vertical asymptote. Here we're going to be able to define what a horizontal asymptote is. So the concept that we have is this. Let's just draw ourselves a picture here. And here's a picture. I can call this f of x. So what I have is I'm telling you that if the limit of f of x as x goes to infinity is equal to L, okay, for L, doesn't say it here, but for L, a real number. L is going to be a real number, okay, not infinity or anything like that. So what's happening is as x moves in this direction to the right, okay, forever and ever and ever, all the way across the cool Google slide here that we have, all right, and the abyss over here in this area, okay, as you move toward the right, the y value approaches L. So the limit actually does approach some y value. So let's call this L. And what happens is, again, as the graph moves in this direction to the right, the y value gets closer and closer and closer and closer to L. Okay? Closer and closer to L, right? So what's happening is, if we look at what's going on at L, well, we basically see this. It's a line that this graph just seems to get closer and closer and closer to, but just doesn't cross. So we call those horizontal asymptotes, right? This is a horizontal asymptote of the graph. Okay, the line y equals L is considered to be a horizontal asymptote of f of x. The same thing holds if x goes to negative infinity. So if I draw my graph here down this way, okay, toward L, and the graph approaches L, the limit goes to L, then we can also say, in that case, that y equals L is a horizontal asymptote. So it doesn't matter whether it approaches infinity, x approaches infinity from the left, or I'm sorry, from x approaches in positive infinity or approaches negative infinity. Okay? If it approaches either of the infinities and the value you get for the limit is a real number, then that line at y equals L is considered to be a horizontal asymptote, right? The line y equals L, okay? Y equals is a horizontal line, right? So that's what we're talking about here. Now, it could also approach from underneath, right? So from underneath this way as well. Okay, what I've drawn here is no longer a function, right? It doesn't pass the vertical line test, but just so you understand, it could also approach from underneath or on top. It doesn't make a difference. All right, but as long as it approaches that y value L, then, okay, there's a horizontal asymptote there. All right, so that is the actual definition of a horizontal asymptote. Okay, so what we're going to do with the rest of our time is we are going to talk about how to actually calculate some limits as x goes to infinity or negative infinity. All right, let's take a look at this first limit. The limit is x goes to infinity of 1 over x. Okay, so if I take infinity and plug it in, okay, in quotes, you really can't plug infinity in. You get 1 over infinity. So the question is, what is 1 over infinity? Well, 1 over infinity is a number that is extremely large, right? So if we have 1 over infinity, we have a number that's extremely large, 1 over a number that's really big. So we're talking about 1 over a million, 1 over a billion, 1 over a trillion. The number is very, very, very small. The overall result So we would say the limit as x goes to infinity of 1 over x is equal to 0. You approach 0. Okay? So 1 over something really big is really small, right? So 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000, right? The larger I make the denominator, the smaller the overall result. Okay, larger denominator means smaller overall result. All right, and eventually you get close to 0. So the limit you approach is 0. All right, now let's try this. Slightly different. The limit as x goes to negative infinity of 1 over x. Well, slightly different, but same result. As x goes to negative infinity of 1 over x, you get 1 over something really big, but really negative. But again, does it really matter? Put negatives in front of all these numbers that we just talked about. Negative 1 over 10, negative 1 over 100, negative 1 over 1,000, negative 1 over 10,000, negative 1 over 100,000. The result still goes to 0. Okay, that result still goes to 0. All right? Okay, so these are the two main limits that you're going to use here to help you on your quest to calculate limits at infinity. Let's take a look at the third one. The limit as x goes to infinity of this. Okay, so to do this, we can apply the limit laws, right? We can take the limit as x goes to infinity of 1 minus the limit as x goes to infinity of 2 over x plus the limit as x goes to infinity of 5 over 3x to the fourth. Okay, so the limit as x goes to infinity of 1, well, there's no x to actually put into this limit, right, in the expression here. So this limit is just 1. Okay, x goes to infinity, it doesn't really matter because the answer is always 1. Minus the limit as x goes to infinity of 2 over x. That's 2 over something really big. So the result is really small. It goes to 0. Plus the limit as x goes to infinity of 5 over 3x to the fourth. Take infinity and put it in here, raise it to the fourth, multiply it by 3. That number is going to be huge. So 5 over that number that's really big is also really small. The result there is 0. So 1 minus 0 plus 0 is 1. So this limit comes out to be 1. There's your correct answer. Okay? So those are 3 simple limits that we're going to be using. Well, 2 of them that we're going to be using, and one of them is like an offshoot of that. All right? Let's keep going. Okay, now let's make it a little bit more interesting. The limit as x goes to negative infinity of 2x squared over x squared plus minus 4. So the first thing that I would try to do is I would try to take negative infinity and substitute it in. So if I take negative infinity and square it, I get positive infinity times 2. Well, that's still going to be some kind of infinity, right? Positive infinity, really big. Over negative infinity, square it, it becomes positive infinity. So it becomes a number that's huge, right? A number that's as long as the math hallway in the high school. Now, if I take that number and I subtract 4, that number that's as long as the hallway in the high school is going to be like, really? So that's all you got? You're going to take 4 away from this thing? That's not going to do anything to me. It's still going to go to positive infinity. So I have infinity over infinity. Infinity over infinity of any type, positive or negative, in both the numerator and the denominator, is indeterminate. Okay? It's an indeterminate form. All right? It's an indeterminate form. Okay? Like 0 over 0. This is our second indeterminate form. And you can understand why it might be indeterminate. At least I hope you can. Infinity divided by infinity. Infinity is a number as long as the hallway. Infinity is another number as long as the hallway underneath. But the question is, how do these two numbers compare to each other, right, to decide where the limit actually goes to? I don't know. I mean, is this number in front of the hallway, or I'm sorry, this first number okay? It's a number as long as the hallway. Is the first number in that number a 9? And the bottom one, the first number, is a 1. So on the top, I have 9 followed by 100 zeros. And underneath, I have a 1 followed by 100 zeros. Or in the numerator, is the number a 1 followed by 100 zeros, and the denominator is a 9 followed by 100 zeros? That would make a difference, right? That would actually make a difference for my final answer, okay? Depending on how big this infinity is compared to this infinity here. So the good news is these are actually pretty easy to determine because you pretty much do the same thing every time. So for infinity over infinity as an indeterminate form, and again, this only works for infinity over infinity, not 0 over 0. Okay, please keep that in mind. It does not work for 0 over 0. Okay, for infinity over infinity, any type, you're going to divide every term by the dominant term. I don't even want to call it the dominant term. I want to call it the dominant power. Okay, I don't even need to call it the term. I just want to divide by the dominant power. All right, so let's talk about what I mean by that. Let's come back over here and look at my example. In the numerator, I have 2x squared. In the denominator, I have x squared minus 4. So ultimately, the power that controls what happens with this function is x squared, right? X squared is the largest power that's in the numerator and also in the denominator. So what I'm going to do is I'm going to rewrite my limit by dividing every term by x squared. I'm going to divide all the terms by x squared. So here the dominant power is x squared. Divide everybody by x squared. Now let's see if we can calculate the limit or clean it up a little bit, and then we'll go calculate it. So in the numerator, we get 2. In the denominator, x squared over x squared is a 1, minus 4 over x squared. Okay, now, x goes to negative infinity. In the numerator, I'm going to get 2. In the denominator, I have 1 minus 4 over x squared as x goes to negative infinity. That's 4 over something really big. So the result is really small. Remember, that's from the last page, right? Okay, so our final result is 2. So the limit as x goes to negative infinity of 2x squared over x squared minus 4 is equal to 2. There's your correct answer. Okay, we got that by dividing by the dominant power, which in the numerator and the denominator was x squared. We divided everybody by x squared, and then we just tried to figure out what limits we needed to. All right, okay, let's try to make it a little bit more complicated here. And we'll keep going. Okay, here's another one. Let's take the limit as x goes to negative infinity of x plus x squared minus 6 over 6x plus 5x squared minus 2x cubed. Okay. All right. So now, first thing that I would do is try to actually take negative infinity and plug it in. I really shouldn't be writing equals here. Let me get rid of it. I should just be trying to determine the limit. So if I put negative infinity in, the thing that ultimately is going to control the numerator is the x squared, right? If I take negative infinity and square it, it's going to be a positive infinity. So in the numerator, I'm going to have a positive infinity. Okay? The x definitely does something, but not as much as, again, take a number as long as the hallway and square it, then compare it to a number that's as long as the hallway. The number that's the number that was squared is going to be way bigger than the number that was just initially there. So in the denominator, the thing that's going to dominate the thing is the 2x cubed, right? Or the x cubed. If I take x cubed, if I take negative infinity and cube it, I'm going to get negative infinity. So I get positive infinity over negative infinity. This is indeterminate. Okay, this is indeterminate. So what we need to do is we need to find the dominant power. So the dominant power is pretty easy to pick out. Okay, the dominant power here is the largest power. Ultimately, at the end of the day, when I have this limit, the largest power is what is ultimately going to decide where this limit is going to go. And if I look at all the powers that I have, the dominant power is the x cubed. It is the largest of the powers that are here. That's the thing that's ultimately going to decide where this limit ends up. So I'm going to divide every term here now by x cubed. Okay? I don't even have to divide by the 2x cubed. I just have to divide by x cubed. All right? And then we'll talk about the fact that you already know this. Yeah, you learned this last year, I think. All right, so I'm just dividing everybody by x cubed here. And then I'm going to try to evaluate. All right, I'm going to clean it up first a little bit. So we have limit as x goes to negative infinity. In the numerator, I have 1 over x squared. I have 1 over x. I have minus 6 over x cubed. Underneath, I have 6 over x squared. I have 5 over x. I have 2. Okay? All right, now I want the limit as x goes to negative infinity of all these things that are here. 1 over x squared as x goes to negative infinity. That's 1 over something really big. The result is really small. It goes to 0. 1 over x as x goes to negative infinity. That's 1 over something really big. That result is really small. It goes to 0. Minus 6 over x cubed as x goes to negative infinity. 6 over something really big is really small. That also goes to 0. 6 over x squared as x goes to negative infinity. 6 over something really big is really small. That goes to 0. 5 over negative infinity, 5 over something really big is really small. That goes to 0. Plus 2. So what do I get? I get 0 over 2. So the result is 0. I'm sorry, not 2. It's 0. Do what I say, not what I write. 0. Okay, so the limit as x goes to negative infinity, my original problem, is 0. That is the limit. All right, now you actually did learn this last year. Okay, you learned it when we talked about horizontal asymptotes, right? Now this also tells me that y equals 0 is a horizontal asymptote of this function f of x, right? Okay, that is telling me that y equals 0 is a horizontal asymptote of f of x. Okay, for the problem on the last page, right, y equals 2 is a horizontal asymptote of that function. All right. I think it was 2. I think 2 was the answer. Okay. Now, you did learn this last year. Last year, you learned that if the powers in the numerator and the denominator were the same, you just took the leading coefficients and divided them. So in the last example, it was 2x squared over x squared minus 4. The degree in the numerator was 2. The degree in the denominator was also 2. So the degrees were the same. So take the leading coefficients, the 2 and the 1, and divide them, and you get 2. And last year we said, okay, so y equals 2 is the horizontal asymptote. That was from the last page. Okay, and then here you have degree 2 in the numerator, degree 3 in the denominator. So the degree in the denominator was larger than the numerator. Right, was bigger than the degree in the numerator. So it was automatic that y equals 0 would be the horizontal asymptote. All right, you didn't understand why, you just kind of accepted it as, yep, that's the rule. I told you, or Miss Adams told you, somebody told you, and you're like, yeah, all right, I'm good with it. Yep, don't need to know anything more about that. Well, now you do. This is why you're getting those answers. Okay? All right. Let's see what else we have in store. I think I know what's next. Let's see. Here we go. Yep. Okay. Let's take the limit as x goes to infinity of the square root of 16x squared plus 5 over 2x minus 3. So if I take positive infinity and plug it in here, so to speak, I get infinity squared times 16 plus 5. Then I got to do the square root of it. But regardless, it's going to infinity. In the denominator, 2 times infinity minus 3 is infinity. This is infinity over infinity. This is indeterminate. So the question is, how are we going to fix it? What is the dominant power? Well, if you look, the dominant power, the issue here is that there's a radical. but it's an x squared that's under a radical. So the square root of x squared is x, right? So it's not really an x squared that you're seeing here in the numerator. It's the square root of that x squared, although you can't take it, okay? The square root of x squared is x, right? In the denominator, it's also x, okay? So the dominant power is x. Now, the issue is to gain access to the x in the numerator where their square root is, we're going to have to call it the square root of x squared, right? Because you can't just randomly divide by x. I'll show you here in a second. So we have the limit then as x goes to infinity. In the denominator, it's easy. It's just 2x over x minus 3 over x. I'm going to divide everybody by the dominant power. In the numerator, I also want to divide by the dominant power. But again, everything that's up there is in a radical. Okay, the 16x squared is in the radical and the 5 is in the radical. You can't just eliminate the radical because it's inconvenient. Okay, it's part of the problem. So rather than we can't just put an x in the radical because the square root of x, if I were to put the square root underneath, wouldn't be the same thing as the square root of x squared. So I need to put the square root of x squared underneath, right? Because I'm in the radical. Now, if I were to do the square root of x squared in the denominator, I'd get x. I'm dividing by the same dominant power that I did in the denominator. Okay? All right, so now let's clean this up and see what we get. We have the square root of 16 plus 5 over x squared over 2 minus 3 over x. I forgot the limit sign. Let me see if I can stick it in here, sort of. All right. Okay, now let's take a look. As x goes to infinity, in the numerator, we have the square root of 16 plus, as x goes to infinity, 5 over something really big is really small. That goes to 0. Over 2 minus 3 over something really big is really small. That goes to 0. So what do we get? We get the square root of 16 over 2, which is 4 over 2, which is 2. So the limit is 2. Y equals 2 is a horizontal asymptote of that graph. Okay? Keep in mind, most common mistake here is that people just throw the radical away. You can't just throw the radical away because the radical is part of the problem. So you have to evaluate with the radical. You got to take the square root of 16. It's not just 16 that's up there. All right? All right. That takes care of that one. Now, the question I think that most people have on their minds is, I would imagine, probably the first question is, when is this video over? But the second question might be, perhaps, is the limit the same from positive infinity as x goes to positive infinity as it is from negative infinity? Okay. Well, let's see. As x goes to negative infinity, the numerator is going to be positive infinity. The denominator is going to be negative infinity. But that doesn't matter. That's still indeterminate. Okay, so I need to divide by the dominant power. So the dominant power, well, it's the same thing that it just was, right? I mean, the square root of x squared is still, it's x squared inside the square root, and underneath it's an x. But it's actually not the same because x is going to negative infinity. So let me explain to you the difference between the one on the left and the one on the right, and what the difference is and how we accommodate for that. Okay? Let's say, for example, I were to ask you what the square root of 9 squared is. Well, square roots are like parentheses. You have to do what's inside the parentheses first, then you can do the square root. So the square root of 9 squared is like doing the square root of 81. The square root of 81 is 9. Okay? If I start with a positive value of x, so x is positive, okay? Oops, I wrote square root 9. X is 9. Square root of 81 is 9. Sorry, folks. You get 9. Okay, I start with a value, x. Here's my x. It's 9. It's positive. What do I get out? I get out the same number, x. I started with x, I end with x. I started with a 9, I end with a 9. Okay? Now, let's take a look what happens if I were to put negative 9 in. Let's talk about the square root of negative 9 squared. Again, radicals are like parentheses. You got to do what's inside first. Negative 9 squared is 81. The square root of 81, and the problem with square roots is you take the principal root, right? You always take the positive root when you're evaluating, okay? When you're solving, it's different. It could be it's plus or minus. But when you're taking the principal root, or when you're evaluating, the square root of 81 is 9, okay? Now, look at what we have. X is negative when I started, right? Here it is. There it is. It's negative 9. But when I finished, it came out positive, okay? It came out as positive, right? It didn't come out as the same x. So if I were to have my x value here, over here on the far right, which happened to be negative 9, well, I don't want negative 9 as the answer. I want 9. So to get 9, I'm going to have to negate the negative 9 to get a positive value, which is the answer I want. So when x goes to negative infinity, if these numbers in here are negative, the final result is going to be a positive. So the number I put in was negative. The number I got out is a positive. So to make sure that these two numbers match, this x and this x, I'm going to have to negate that x. Okay? I don't have to do it over here because of this example here. I put a positive 9 in, I got a positive 9 out. I put a positive x in, I got the same number out. So these two x's are equal to each other. So I don't care. I'm fine with that. Okay? The problem here is I put a negative number in, I got a positive number out. I need to make sure that this number and this number, okay, come out to be the same. Right? This number and this number come out to be the same. So I put an x in, that was negative. I got a positive number out. So I have to take the negative of it to make this negative match this number that's on the right-hand side. Okay? So this is definitely a little bit trickier. All right, now, so we have our dominant power. Our dominant power is the fact that, let me just erase the rest of this, folks. The square root of x squared is now equal to negative x, okay, not positive x anymore. All right, now I'm just going to divide. All right, do the same thing that I just did. Going to divide everybody by the dominant term. Here we go. So x goes to negative infinity. Divide everybody by the dominant term. Inside the radical, 16x squared. Going to divide by x squared. And I'm going to divide 5 by x squared as well. Underneath 2x, I'm going to divide, but I'm not going to divide by x. I'm going to divide by negative x because I needed that negative to account for the fact that I was going to negative infinity. So these numbers were going to be negatives. Minus, what number is it? 3 over also a negative x. I can clean this up a little bit. But look what we come out with. We get the square root of 16 plus 5 over x squared over, the whole thing's in the square root there, negative 2 plus 3 over x. All right, so now the limit as x goes to negative infinity. In the numerator, I have the square root of 16 plus 5 over something really big is really small, goes to 0. Underneath, negative 2. 3 over something really big is really small, goes to 0. So I have the square root of 16 over negative 2, which is 4 over negative 2, which is negative 2. So my answer now is negative 2. Okay? All right, so here is the rule of thumb. For the most part, there are only a couple of cases where you would have to find the limit or the limit from as you go to negative infinity would be different from the limit as you go to positive infinity. Radicals is 1. That's a place where the limit as x goes to positive infinity and negative infinity, can be different. The other one is in exponential functions. Okay, so if you have an x in the exponent, that also could be an issue. All right, that also could be an issue that you'd have to consider. Anything else, any other rational function like the two that we did previous on the previous 2 slides, it doesn't matter whether you approach x from negative infinity or x approaches to negative infinity or positive infinity, the value of the limit will be the same. Okay, the value of the limit will be the same on those. This, it's possible that they could be different because of the radical. And like I said, the other one is exponential functions. That's also possible. All right, let's take a look at 2 more examples here, okay, real quickly. So let's talk about the limit as x goes to infinity of sine x. All right, so if I take infinity and plug it in, I get sine infinity, whatever that means. All right, that I have no idea what that is. Now, the thing is, it's not indeterminate because there's no denominator on it, right? There's no denominator on this. So the limit must be determined. Okay, I'm not going to get 0 over 0 or infinity over infinity. There's no denominator to give me another infinity. So what I need to do is just think about what the graph of sine x looks like. As x goes to infinity this way, right? I want to know what y value I approach. Okay, what y value am I walking toward? Well, I'm not really walking toward any y value. I just keep going back and forth between -1 and 1. So this is an oscillating limit. So this limit simply does not exist. Okay, there is one example of an oscillating limit where you can write dne. All right, that we learned about last year, oscillating limits. Okay, so this limit does not exist at all. All right, now let's come over here though. Let's make it a little more interesting. The limit as x goes to infinity of cosine x over x. So if I plug in infinity, so to speak, to the numerator, I get cosine infinity, which is probably dne, right? And underneath, I'd get infinity. dne over infinity. Well, it's not indeterminate, but I have no idea what that is, right? What is dne over infinity? Okay, now there's a couple ways that you can argue this limit to me, all right? I'm going to show you one, but you could argue for something, well, the value is going to be the same, but you can argue the argument slightly differently if you wanted to. So I am going to say this. I know something about cosine x. Its value is between -1 and 1, right? Cosine's the x coordinate. I'm on that unit circle again. I know the x coordinate's never going to be bigger than 1. It's never going to be smaller than -1. So cosine x must be between -1 and 1. So now, you might already see what I'm attempting to do here. I'd like to try to get this limit, or this expression in the middle here. So I'm going to divide everybody by x. And I'm going to see if that helps me at all. Divide everybody by x. Here we go. Okay. And now I'm going to try to take the limit as x goes to infinity of -1 over x. The limit as x goes to infinity. And you should be able to see where I'm going with this. Cosine x over x. And the limit as x goes to infinity of 1 over x. The limit as x goes to infinity of -1 over x. 1 over something really big is something really small. This goes to 0. This last limit as x goes to infinity of 1 over x. 1 over something really big is really small. This goes to 0. Well, the one limit goes to 0. The other limit on the outside goes to 0. So I guess the middle limit must go to 0. And I know that because of the squeeze theorem. Okay, so there's a great example of the squeeze theorem being used out there in the wild, so to speak. Yeah, just randomly, there it is. You can use the squeeze theorem to come up with that. Okay, so this limit comes out to be 0. All right, So again, dne over infinity means nothing to me. It's not indeterminate. You need to figure out some way to get the value of the limit. And this is one way to do it. Okay? All right, that's it for today. I hope you enjoy those questions and you like the whole video. This is it for chapter 1. And the next time I see you will be at chapter 2. All right? Thanks for clicking.